All right, so I wanted to develop a bit of intuition for why the rate of change of area might be equal to the value of the function at any point. So that was the first part of the fundamental theorem of calculus that we spoke about. Basically, we said as the area changes, the rate of change of area will be equal to the value of the function itself at that point. And that was sort of a key insight. It's a bit tricky to wrap your head around. So sometimes a good thing to do is to think of a really simple example to sort of make it a bit more concrete. So if we think about this green line is just the function y equals 4. And what we're going to do is we're going to take the integral from 0 to 10, and we'll see what happens as we do that. We're going to create some area underneath this graph. So if we let that play, I can tell you that every time it increases the x along what's actually the t-axis on the bottom, I'll explain why. Every time that we go across one unit here, that's what equal to 1 second. So overall, that took 10 seconds to fill the entire area, and we can see we've just got a rectangle with a length of 10 and a height of 4. So that total area is 40. Okay, let's just point something out. If we think about what the gradient of a function is, most basically it's just a rate, right? So we're saying the change in area over the change in time. So let's bring our slider back to 5. We can see here that when, after 5 seconds have passed, the area is 20. And then after 8 seconds have passed, the area is 32. So the change in area, or delta A, is 12 divided by the change in time, which is 3, which is equal to 4. Now that's interesting because something to think about here is the fact that the rate of change of area is always constant. Because we've got a nice simple function, you can sort of think of the area being filled up at a constant rate. So what's interesting is, yeah, at any point, so say at this point here, the rate at which the area is changing is equal to the value of the function at that point, which happens to be 4. And then similarly at this point here, after 8 seconds, again, it's still filling up at the same rate, or the area is increasing at the same rate, which also happens to be 4. And similarly, obviously, if we do it as an average rate of change between both of these points, it obviously turns out to be 4 as well. So yeah, you can see how the rate of change of area is sort of linked to the value of the function at the point t, or at that time t. Let's look at another example that's a bit more trickier. So if we look at a linear example, again, what we'll do is we'll let the animation play, and I can tell you that this is taking 10 seconds. So, and then we'll think about what's going on. So as you can see, we've got a few different points here. We've got some point here, 5, 10. And I'll just point out as well that this is the line of y equals 2x. So this point here is at 5, 10. This point here is at 10, 20. I encourage you to think about how the area increases as we go along. You might notice in the first 5 seconds that the area only increases from 0 to 25. But in the 5 seconds after that, from 5 to 10, the area goes all the way up to 100. So we can see that in the first 5 seconds, it was an increase of 25. But in the 5 seconds after that, there was an increase of 75. So what we can say is the change in area. So from the change in area from 25 to 100 is 100 minus 25, which is 75. And that took 5 seconds, which gives us a rate of change of area of 15. You think about the units, we could say something like 15 centimeters squared per second. Okay, now you're probably wondering, what does that 15 have to do with things? Well, since we took an average rate of change between 5 and 10 seconds, the middle point there would be 7.5 seconds. And lo and behold, the value of the function, 2x at 7.5, is 15. So again, the rate of change of area at any single point is equal to the value of the function at that point. Okay, and hopefully this taking an average rate of change here sort of helped, because at this middle point, the rate of change, you can sort of think of it, the rate at which the area is filling up is 15. And similarly here, you could get the average, you'd get the rate of change after 5 seconds being 10, and after 10 seconds, the rate of change of area is 20. So sort of building that intuition for why the gradient of the area function is equal to the value of the function at that point.